finger. So Tuesday is the dual captain. BC test has some easy questions, so they actually kind of design it so that they go together. So some questions. Hold on. It was in what was turned in. Oh, it's on my desk. Alright. Kudos! There is a page on the screen that you're supposed to be writing down. Yeah. I will not give you much time. Once I get to the front, I'm grading Alyssa's notes really quickly so that she can join us. But you guys need to focus. This is, I literally want you to call it Intro to Chapter 12. Intro to Chapter 12. I know it's awkward. You can call it 12.0 if you want. Ooh, go team.
Electrical set.
I suppose. But I figured 12.0 sounds a little 12.I for intro. Sure. 12P for preview. I don't know. You do you. I just want it in there. Because I want you guys to define calculus as the mathematics of change. Dun, dun, dun. Alright, let's let them write it down back here before. HonorsPrecalc should be done by then. Honors check. Alright. Why are you telling someone to be quiet?
Oh my god.
You guys make it so much worse than it could have just been like, oh, you're like
Nice little roast. Cheers. Yeah, little roast.
Alright. We might do some more preview of calculus stuff. However, I don't give you guys as much visualization, as much background, as much history and whatnot as regular pre-calc because I just want you guys to get into actually being able to solve stuff. If you do join Calc AB next year, we do a lot of that sort of stuff to start the class once everyone is together, like transfer students, new international students, like students from regular pre-calc, honors pre-calc, my classes, Mr. Chase classes all together. So we're just kind of like, we're doing a preview, but not like a full preview. Let's get excited about calculus. It's more kind of like, okay, here's a few things calculus does, why it's a thing. But let's get into learning the basics, the foundation, the beginning. I want to let you guys know that because it's not going to be like bells and whistles and balloons flying in the ceiling. That's next year. So, preview calculus, intro to chapter 12. There's the bell for somebody in middle school. Calc is all about quantities moving, quantities changing. The way they put it up there, I put it up there, I think I actually typed that out. Math before calculus is static, whereas calculus is dynamic. In calculus, the math that is involved or that formed the foundation of calculus grew out of a need to be able to model quantities that are always moving and changing. That works in physics. Quantities are always moving and changing in the sense of motion, literally seeing things move. In physics, you also have electricity. That's kind of a little different. You don't necessarily see electricity moving and changing. Calculus is a huge, or is applied in big ways in the economics field recently. Econ has tons of calculus working on it as far as the trends and as far as rates that are going on at different times, et cetera, et cetera. Biology, chemistry has calculus for sure. bio, not quite as much as far as what's going on, but we know that a lot of these different fields have a lot of tech and technology going on in them, and that comes back to a lot of math as well. So even though calculus is important, it's not so much that calculus is the end, it's more like calculus is the means to broaden all these different fields. Calculus had a lot to do, or actually I guess fractals, had a lot to do with like medical imaging, with animation and CGI and all that sort of stuff. So there's all kinds of different applications to math in general, but calculus especially kind of just really opened the field in back in the 1600s, but started even before that, as far as becoming a thing. But that was just a little baby peek. Let me show you some specific things that before calculus we could, after calculus we can't. Okay? Before calculus we could, after calculus we can't. Before calculus, or before the concepts in calculus, you could plug in an x value into a function, get out a y value, no big deal. But after calculus, or with calculus, we could figure out what's going on at a point even if it doesn't exist. Now, you guys have learned things like how to find holes. You've learned things that actually need calculus, but you've learned little tricks that have helped you kind of avoid it up until this point. Before calculus, we were able to have 2 points and figure out the slope of a line, but that's boring. A line has to have constant rate. That's not life, that's not motion. Rates are never constant. Even cruise control, it's not constant. Kind of it is, but not really. Slope of a curve, much more applicable. The rates are always changing. The slopes are always changing. What is the rate? How fast is it going at 1 point specifically? Not average over 2 points, but instantaneous at 1 point. Okay, that's this one. If you have some curve, not just a parabola, we learned about the focus and how you can find a tangent line of a parabola, but any curved motion, any curved trend. You could have found the slope of the secant line that goes through the curve, but now we can find the slope of the secant line, not just to a parabola like we learned, or to a circle in geometry, but to anything that's curved. We already talked about the average versus the instantaneous rates. That's all stuff to do with rates, stuff to do with kind of geometry-ish. In geometry, you kind of learn how to do the curvature of a circle, but now we do the curvature or the arc length, maybe a better way of saying it, of any curve. Figure out the height of a curve at. This one we can find the max. Ooh, without our calculator, we can find the maximum not just of a parabola, but of any curved function, any curved quantity. We can find the max with calculus. Before, you could find a tangent plane to the sphere with geometry, but now you can find a tangent plane to any surface. And then you can find direction along a line, think like with forces and gravities and whatnot. You could talk about direction along a straight line. Now we can talk about direction going off of a curve, like projectile motion kind of. Not projectile. What am I trying to say? Centripetal motion. Okay. We talked about it. I forget the word for it. Without calculus, area of a rectangle, no big deal, memorize geometry formulas. With calculus, area of non-geometric figures, area under the curve. Before calculus, worked done by a constant force, but now a varying force, much more applicable as well. Center of a geometric figure, we could do without. Centroid in any sort of region. Length of a line versus length of an arc. We could find volume with geometry, memorizing some formulas. Technically, they come back to calculus as well. Volumes and surface areas of just geometric ones. You only have so many we can actually do. But in life, there are so many more figures that are not just geometric. So how do you deal with those calculus? Also densities, not just surface area and volume, but densities. If you have the mass of a solid with constant density, I guess we could do that with calculus. But varying density, you need calculus. The last one, series is one. You didn't need to necessarily write all the stuff I just showed you. I was just going to show you without calculus and with calculus. But these next two things I do want you to write because they're the two main problems that all of the foundation revolve around solving. The two main problems that the foundation of calculus, the basics of calculus, all revolve around solving. In a way, you could say these were the two big questions that were unanswered that led to the discovery of calculus. The nice thing is we've already talked about the tangent line problem with quadratics. I already kind of introduced the idea of the dilemma, but now we're just broadening it so it's not just to do with quadratics anymore. If calculus only helped us with quadratics, it would still be extremely limited, but it doesn't. So I want you guys to go ahead and make sure that even though this looks like a parabola, I want you to actually continue the graph on the left so that it's not a parabola. Make it something else. If it was a parabola, we could use all the crazy focus stuff that we did in section 9.2. No, 10.2. I want you to go ahead and make it, I don't know, cubic. Make it like a quartic if you want. Make it something that's not just a parabola. Because a parabola, there actually is a way to solve it, a tangent line and the focus. The distance formula, all that jazz. Make it something else besides a parabola. Once you guys have that one, there's one other problem as well. But before we get to the second problem, I want you guys to write down, even though it's going to look complicated, this is technically not even with pre-calc, it's just with non-calc. This is with algebra. This is with algebra 1, algebra 2. How will we find the slope between 2 points? Let me give you a second. There's a lot of notation on the board. If it wasn't important, I wouldn't make you write it. These delta x's you guys have seen before in slope formulas, delta y over delta x. But you haven't seen used like this before. What did you say, Luca? Yeah, is what we've done before, but delta x is getting applied a little bit more now, which maybe it should have always been, but back in Algebra 1, you probably weren't ready to see some of this. No, you're ready. It'll be okay. Come on.
Brandon's off for 4 months with the cast. And he went to the doctor.
He just went to the doctor?
Yeah, he got a cast.
I told him.
His foot kept on breaking.
Yeah, because as he keeps walking on it, he did more damage. I told him as soon as you get back to that boy.
How about 2 weeks?
Yeah. Is it the fifth metatarsal, Luca? The one on the far end? Can you tell you? Was it like...
I'm not sure, but it's because he kept on breaking. He didn't even get a boot. Or cast.
So that was me, and I only walked down mine like half a day, and even then it was public. We'll see what it is in high school.
Oh no.
Because someone down in Mexico had him like stomp his foot and was like, no, I just pulled something. And it hurt a crap. And it hurts right there and it's swelling like that. It's just like Are you guys guys all? Okay. Don't worry. As you guys are writing, I want to hopefully alleviate some of the stress. Delta x is a change in x's, right? Wouldn't that be a horizontal distance? One x minus another x is how far in between? Right? Okay, so delta x being the run, this one kind of makes sense. Where does it get complicated? This one. We're used to delta x, and Luke, as you and I were saying earlier, what would this one have been called?
Delta Y.
And this is delta y. Why is that just a more particular, a more drawn out, a more specific way of writing delta y? How do I know it's delta y? It's the change from P to Q. That's true. It's the change from P to Q of what values?
Isn't it pretty much
The y values.
f of x, but they're the c's and they'll subtract out?
Yeah, and f of x are y values, right?
Yeah.
So you really just have one y value minus another y value, but the reason it's so complicated is because they are not arbitrary, I shouldn't say that. They are general y values. They're not specific y values. We're not just trying to do calculus with two random points of one specific curve. We're trying to generalize it for everything. Sorry, we're leading up to calculus. In our earlier, in algebra, probably we're talking about slopes between 2 points all along since algebra 1. So what you guys were always technically doing was saying, hey, I have two different points. I have a Q and I have a P. And the Q and the P can both be seen with an x value and a y value. In leading up to calculus, we would start with one particular point, which is why P has like an actual x value C, and the y value would be f of C. And then we're saying that the second point is some distance away from C, and that distance away would be the delta x. That's how far away it is. And then if C plus delta x gets us to our second point, then we can go ahead and plug in C plus delta x to our function, get our y value. And if we subtract our two y values, we get our delta y. If we subtract our two x values, we get our delta x. So this really does come back to what you guys have simplistically memorized for quite a long time. That slope is equal to delta y over delta x. However, if we were to use all of this notation, it would be a little bit different because it would be written f of, if we know a particular point, C plus delta x minus f of C all over. That looks a little different. By something called the difference quotient.
What's the point of writing the delta y like that? Because if you distribute the f to c, you're gonna
Function
subtract out.
notation. So function notation is saying plug in the C plus delta x into f. I can't just say f of f. Because f is not a number. If f was a number, we could distribute that. But since f is a notation, distribution, it doesn't mean multiplication. Does that make sense? It's not f times, it's f of. Different idea. So that's pre-calc. Calculus says, okay, cool, so you have this formula that you can find a slope between any 2 points. Let's use that over and over and over and over. Let's use that over and over and over and over. And let's say, okay, let's use that formula to say, okay, I can find that slope, but I want this tangent line slope. That is my goal. That's what we said our main problem was, to find a tangent line slope. So we say, okay, well, that's cool. We can find the slope between P and Q, but that's not good enough. I need to get closer. And I need to get closer. And I need to get closer. And what's going on to these lines, guys, as we come down, as the arrow shows, as we come down and as the point Q gets closer and closer and closer to P, what's going to happen to each of those lines? The slope is going to be smaller, and it's not going to go smaller forever. It's not going to randomly start going negative. It's getting closer and closer and closer and closer and closer to this slope. Because I'm confined by this P. I need the P. The P is the point of tangency. From this point, I just need to get closer and closer. So what would I do next? Probably cut that in half, and cut that in half, and cut that in half, and cut that in half. Hey, that sounds like me and Cody getting closer and closer and closer. Yeah. Whole conversion idea comes back.
So it's like notation. Remember A1 plus A2 and gets plus 1.
So this time we're not adding. Because we're not trying to add, like accumulate them, we're not trying to add them all together. That comes in the second big problem in calculus. This one, we're trying to see just what are the slopes, what number is the slope getting closer and closer to? What number is it approaching to? Not adding them all together, but just instead seeing what's happening. Where is it going? And that's going to be with something to call. Second big problem. Second big problem. Area. How do you find the area of that?
You get a measuring stick.
Okay. You can get a measuring stick. What do you do? Okay, that'd be volume.
Okay, sure.
We can't do that with everything.
You can divide sections.
Yeah, you can divide it. Like, for instance, can't we make that a point?
Yeah,
That'd be a rectangle, right?
right.
So if we could figure out, no, that would be some sort of f of a value. So f of a would be the height. A minus b would be the base. But Nicole asked a very good question. That gives like an approximate. But what about the stuff on top? Maybe. Kind of like
What if you do a circle shape?
But this is getting kind of imprecise, right?
We're not paying this.
Another rectangle. Okay, so then Karina's like, well, if you do another rectangle, go here. And then maybe be like half
Oh,
inch.
that looks legit, yeah. That's legit.
Well,
Well,
but would that work for all
Maybe.
functions?
it's not,
Okay,
it's not right.
so what if I
It's
give you
legit, it's a
something
pretty
like-
good idea. Yeah.
What if I give you something like this? Practice. Now what?
Get your measuring stick out. You take.
Now you make a big rectangle, a little rectangle,
Okay.
and a medium rectangle.
Here's the dilemma. Your guys' strategy is a way for approximating, just get rid of all that, is a way for approximating on this one shape. Your way works for one shape. What is our goal, one shape? No. Math, we like a formula that works over and over and over and over again. So how could we do this in a strategic way that could work for any shape, at least as far as estimating? Don't go across, go up and down. Hold on, was there anything else? Do a little shade and do area under curve. The problem is to find the area under a curve that is not a geometric shape. So it's not a circle, not a semicircle, not a quarter circle, not a something smaller than a quarter circle. Not a sector. Hey, that's in geometry, right? Area of a sector.
Ooh,
Ah!
I remember the word, but I never how to.
But the area under any curve, not just the ones that make geometric shapes. With pre-cal, we could say, okay, throw in 4 rectangles. Maybe this one's a little more strategic, because you just split up, and you just say, hey, go hit the curve, go hit the curve, go hit the curve, go hit the curve. Ask the calculus kid about this. Hopefully they can teach Riemann sums to you. Sure. Riemann, R-I-E-M-A-N-N. This guy. Anyway. I think he wrote a book that had the math in it. Sometimes people get attributed things because they wrote a book and they put it in. Like way back in the day. Whether or not they actually found it. But, kiddos, this is not the exact area. I'm not really sure the other one was the exact area either. It looked really close. And that one only worked for one picture. This idea worked with all pictures in the sense that whatever you have, you could go up and hit the curve and make little rectangles of whatever shape. Or similarly go down. That's a whole other question for a whole other day. But with pre-cal, we could say, hey, let's figure out in between A and B, let's split it into 4 equal sections. So we would do B minus A over 4 to get that distance between. And then we'd say, what is f of A? Because f of A would get me the height for this one. What is f of A plus delta x, whatever that would be. So f of A plus, I'll just put delta x. And then this one would be f of A plus 2 delta x's. one would be, why are they all so close together? F of A plus 3 delta x's. Anyway, long story short, we could do the little bases being the delta x's. We do b minus a, cut it into 4s. We could find little bases, we could find little heights by plugging into our function. Or we could go ahead and do base times height for the first, base times height for the second, base times height for the third, base times height for the fourth. Calculus says, that's not stop at 4. What happens if we do even
Make a bunch of
more?
times.
That's a lot.
Let's do 8. Then
Unnecessary
let's do 16. Then let's do 32. Then let's do 64. Then let's add the number of rectangles approach infinity. Approach. And see if the number representing the area converges. Even though we can't literally fit in by hand an infinite number of little baby, super thin rectangles, we can't fit in infinitely many.
Did you know the same width?
Well, these ones wouldn't be the same width, right? Because we take that same finite distance from A to B and we cut it into 8ths. Then we would cut it into 16ths. They'd be even half as wide and half as wide. We can only deal with real numbers. The calculus lets us say, but as we deal with the real numbers, if we can approach what we can't do, and if it converges, we can say that it exists. Calculus makes the leap from what we can do what we can't. So once again, with limits, we wouldn't even stop at 8. We would go from 8 rectangles to 16 rectangles, which means they'd even get, do you guys see how they're all closer now? Right? If we went to 16 rectangles instead, if we went to 32 rectangles instead, if we went to 64 rectangles instead, it would just keep getting closer and closer and closer and closer and a better and better and better approximation. And at some point, do we really care if it's 0.0000 something off? So then we say, hey, I think I know what the answer is going to be. But do you guys notice how both of those problems there was one thing in common? We have to approach an infinite number of rectangles. We can't do that. We have to just kind of think about what's going to happen as we go towards infinity, or infinitely many rectangles, which as we go towards infinity, their bases go towards 0. Or this one, we can't literally find the slope of a tangent line, a slope with only one point, but what we can do is approach the tangent line and see if we can see if the answer is converging, if the slopes of the secant lines are converging. What's in common? Calculus hates limits. The two huge problems upon which the foundation is formed from the two big problems in their answers. And upon that, all these applications come. Calculus comes from limits, is a limits machine. Well, we better learn about section 12.1. Let's learn about them.
Let's do it.
Yeah, new page. The end of last one was calculus is a limits machine. Dot, dot, dot. So limits. Here we go.
Looks like
Yeah.
Is this why this book is called Pre-Calculus with Limits? Wait, is it with limits?
Because we have chapter 12. Other pre-calculus books may stop earlier and not do limits. So basically, you can think about our pre-cal book starts teaching calculus at the end. Our pre-cal book actually starts teaching calculus at the end. Intro.
Does you guys spell into with the U? Next
Now, kiddos, what you are writing does have a lot of words, but I would still call it an informal definition. A formal definition, let's just say no one would like to see. There might be epsilons and deltas and all sorts of other letters.
Yes, I love Greek. Just love it.
Now, you guys notice I've made a few things bold, not because necessarily the definition says make them bold, but I'm going to talk about them off to the left. The main players in this informal definition is F, L, X, and A. The main players are F of X, L, X, and A. They're all variables representative of. I'll fill it in a second. If F of X becomes arbitrarily close to a single number, L, as x approaches A from either side, P.S. underline, either side, the limit of f of x as x approaches A is L. So guys, what we're doing in 12.1 and even 12.2 and maybe even 12.3, we're not necessarily answering the two big questions of calculus yet, but we are learning the mechanism that allows us to even approach the answers of those two big questions from which so much comes. If you look and if you read f of x, should we think x's or y's? What kind of value is this? It's a function value, right? So if f is getting close to L, well wait, in order for a y to get close to someone, what must he be? L must be a not a function. He's a constant. Or he's representative of a constant. But if the y's are getting close to that constant must be a
Real number.
what kind of coordinate must it be? If the y's, if the function values are getting close to it, what kind of coordinate must it be? One more time. If f of x is getting close to L, and f of x are the y values, then what kind of value must L be? A y value. No. Here's a little bit. I thought that would come easier. Anyway, if f of x is a y value, then L must be a y value also, right? Now, f of x is not just one y value, right? F of x is a function of y values. But if the f of x values or the y values are approaching L, then L must be a y value also. And if x, which is the next value, is approaching A, then A must be an x value also. Does that make sense? Sometimes the words just get really confusing. You're like, what on earth is going on? But okay, L is a y value, A is an x value. That's what I was trying to draw the correlation to. And then down below, I take this informal definition and I start putting symbols in. I don't know about you, but if I can simplify the words, the symbols, maybe it'll start making a little more sense. The limit, who I'm trying to figure out, the limit of f of x as x approaches A. Oh, I'm literally just kind of taking the word approaches and replacing it with an arrow, which we've done this year, right? The limit of f of x as x goes to A is L. Or to make that even easier, f of x goes to L as x goes to A if the limit exists. Which it doesn't always exist. If you guys are ever watching Mean Girls, you know
It doesn't exist. It doesn't exist.
well, she didn't know math and solving, so I can't say about that. She just remembered that is a possible answer, I'll guess it.
We actually, John, Murphy, and Connor, they actually did the math. It was funny.
You were very proud of that moment. So, kiddos, haven't we seen where I'm leading you to before? Haven't we written for the sum of infinite geometric series? We only wrote it once or twice, and I didn't make you guys write it again and again. But we have written this before. If the limit exists, then the function will approach L as x approaches A from either side. Remember, you underline that up above. There is notation, but I'm just not throwing it all on you at once. If the limit exists, the function will approach its y value, or this particular y value L, as x approaches A. Another way of saying it is the limit as x approaches A of f of x is L. And sometimes L exists. Sometimes L does not exist. Sometimes the limit exists, sometimes the limit does not. Verbally then. How can I translate the limit of f of x? How I want you to read this from now on. The limit of who? F of as what? As
Y.
x is approaching. X is doing the approaching. We're trying to figure out what is y doing. The limit of who? Of a function. As what is going on? X is approaching who? A. Is. Well, the better question is, most questions in math, they don't give you the answers, right? So the better way of saying it is if this equals L is not there, you are trying to find the L, you are trying not to take the L, find the L, find the limit as x approaches a of f of x. So I could say that interchangeably. I'm used to saying the limit as x approaches a of f of x, but as you're getting used to it, I'll probably say the limit of f of x, so you know who we're looking at, but as x approaches a. Those two statements can be interchanged, but we're looking for the limit of a function as x approaches a. This page, introduce notation on the bottom half, and have informal definition on the top half. If we go back to the top half for just 1 second, the limit is going to exist if f of x becomes arbitrarily close to L as x approaches from either side. So there are some details that aren't in this notation. But what we're trying to look for is there an L? Is there a y value? The function is getting closer and closer to as the x's get closer and closer to this particular L. Okay? A lot of intro, a lot of time on this page. Do we have it all written down? Yes. Did you guys circle your limit?
Yes.
Do you know how to read it if I ask you to read it?
Yes.
Quick illustrations of limits. Yes, don't start your homework tonight. We're going to do fractions instead. Don't start your homework. We're going to do fractions instead.
Dude, that reminds me of this.
There's some intense collaboration going on over here.
It's
Okay. A limit in action. We already saw it 2 chapters ago when we talked about 0.1 plus 600 plus 6,000 plus 6 10,000
plus 6 a million.
Yeah. Wait. So 1/6 we know is the answer. 1/6, the fraction you could have learned in kindergarten. 6. Here's a pizza. Cut it in 6. Here's one of them. But it really has this calculus concept entrenched in it, in the decimal form. Because we would say it's 0.1 plus, remember how we could say that our a sub 1 is equal to 6 over 100, and our r is equal to 1/10, right? And then we could say this is going to exist because the limit as n goes to infinity of s sub n, where we have a sub 1, 6 over 100, times 1 minus 1/10 to the n all over 1 minus 1/10. And remember how I told you, without really explaining too much, hey, as you go to infinity, this thing is going to go to 0, because 0.1 to the power of 1 to the power of 2 to the power of 10 to the power of 100, I was having you solve the limit. And that's how we were able to get to our final answer on this side, on the right-hand side of 0.1 plus 6 over 100 times, did I not do 1/10 on the bottom? Did not do 1/10. 1 over 1/10, 1 minus 1/10 is 9/10. Which is the same thing as 10/9, which is the same thing as multiply top and bottom by 9 over 9. I get 15 over 90. And what does 15 over 90 equal? How do you know it's 1/6? That's a good question. Anyways, do you see the calculus just kind of randomly hidden in there?
Yeah.
So, calculus is in repeating decimals. Calculus is in
All things.
everything. The crazy guy that likes to do all the geometric figures, where there's infinitely or later representation of infinitely many fishes confined in a set of space.
All around us.
Or, well, that's a whole other thing about fractions.
Oh, whoa, whoa.
Tomorrow, we're going to start solving them.
Nature.
Yes! We're going to do tables first, math second, algebra third. It's going to be fun. Yeah, we did words today. Hurry up if you do
Come on, Kristen. Come on. Traffic.
We made it, y'all. We made it out of the free. We made it out of the free.
Yes.
You know, just think about it.
So are you ready for this?
No. Yeah. How do you get my
Oh, you're VP?
Yeah. I was